So this tutorial is going to be on simulating a 2D perovskite device. We're going to be doing a 2D optical simulation, a 2D electrical simulation. For the optical simulation we're going to be using FDTD, and for the electrical simulation we're going to be using a 2D Drift-Diffusion model. These are run one after each other to simulate the optical and electrical properties of this perovskite solar cell. The software we're going to be using for this today is called OghmaNano. And you can download it from oghma-nano.com/download.php, and there you can see we're currently using version 8.1.082. They're updated quite regularly, so it's worth making sure you've got the latest version. So why are we doing a 2D simulation? Well, the thing that's quite interesting about this particular MAPI perovskite device is we've got this light capturing structure on the top of it, which is a series of triangles. And they're about 150 nanometers high and about 150 nanometers wide. And this sort of thing's done quite typically on silicon to try and silicon solar cells to try and improve light capturing. So because of this structure, the thing is no longer a 1D simulation, so standard 1D models won't be able to sort of capture what's going on optically. So you can access this simulation by clicking on New Simulation, FDTD Examples, and then Perovskite FDTD. And the best way to sort of understand what's going on is just to click on the play button and let the simulation run. The first thing it does is it runs an optical simulation called calibration without the device in the scene. And this is effectively to try and mitigate the effects of the simulation window on the simulation results. And then once it's done that, it puts the device back in the simulation in the second run here, and it tries to figure out how much light is absorbed in the device using FDTD. The colour of this text is green, which signifies we're using green light. So in this example, we're just using 500 odd nanometers. You could use, I'll just go back to this, you could use multiple wavelengths to capture the solar spectrum, and it's very easy to do, but it just slightly slow down the simulation. In fact, I'll just show you how to do that if you want to. So if you go to the optical tab, optical mesh, and you set wavelength points to currently to 1. So it's about 550. If you set that to say 20, it will go over the whole of the solar spectrum. But I'll just pop that back there because I don't want the run times to be too long. So we run our simulation, and then at the end, after it's finished the optical simulation, so the FDTD, it will run a JV curve using the Drift-Diffusion model in 2D, and you can see we've got negative current and then we get positive current, so VOC somewhere about there. And the total runtime for this was about 35 seconds, which is relatively long for this sort of simulation. Well, it is relatively long compared to a 1D Drift-Diffusion simulation that takes seconds, or so sub-seconds. So this is, if you're running a lot of these simulations, there is some computational cost for going to 2D, which we'll talk about a bit more later. So once we run it, the main result we get is this. Well, let's look at device.csv first. So what this is just a map of triangles of effectively how the simulator sees the device. And you can see it's how the device is built up of a series of triangles that it meshes. You've got the FDTD grid there, and you've got this detector, which I'll talk about in a minute. So the green thing is a detector, effectively detecting how much light passes from the top of the simulation into the device. So if we just have a bit of a look at this in detail, we've got photons on the top, we've got FDTD grid here, and we've got our detector measuring how much light gets into our simulation. And the result of that is, if we look at g.csv, we get the generation profile within our perovskite, and it's slightly asymmetric. Well, it's symmetric, but it's not quite uniform because there's some diffraction with light when you have a slit. And you might think, well, where's the optical slit? Well, the thing is, our simulation is only, let's see how wide it is. So our simulation's, say, 2 microns wide, so we're going to get a little bit of optical diffraction there, and that's just the nature of solving FDTD and Maxwell's equations. So we've got the generation profile here, and we can project that onto our device in 3D, so just see how it would look in space. And we can turn it back on our device. So if we show our device, we can see where that light's absorbed within our device. So that's good. And then the other major result, I guess, is the JV curve, which is the result of all this computation, and we can see we've got a JB curve with a JSC of just over 150 amps per meter squared and a VOC over about just like 1.1 volts. And this is typical of a perovskite device. So just let's dig back into this a little bit more. So let's just try and examine what happened with the FDTD a bit. So if we look at FDTD snapshots, we can actually examine the fields within the device. So if you click Add, and we can choose which field we want to look at, so EX, EY or EZ, these are the electric fields in Maxwell's equations, or we can look at the power density, which is calculated using the Poynting vector. And then if we make this bigger, and let's make the FDTD grid disappear, and maybe make the detector disappear too, we can step through time steps of this and see what happens to the power as it enters our device. So you can see the waves, and we're not plotting every single time step, we're plotting every 100 or so. So it does jump a little bit, it doesn't look super smooth, and that's just to save disk space. And you can see so the waves are propagating from our source, hitting our structures, and you can see they're definitely affecting the field the optical field as it propagates into our device. You can see some escape round here, round the edges. Yeah. So that's the generation and how the power. Oh, and it should also be noticed that this generation profile is a time averaged version of not the power but the power that's absorbed in the device. So this effectively collapses down to the j.csv. So that's got us effectively down to this part of the simulation, and we've generated our g.csv file. We now run the electrical solver, and the detailed results can be in snapshots. So if we look in the snapshots, we can add the output from the electrical solver. So let's add the conduction band, so LUMO, depending, if you're doing organics, this would be LUMO, and then we've got the valence band, and then let's add in, say, some N Fermi levels and some P Fermi levels, and then we can step through this in time, and in voltage this time, and you can see the voltage up there. So you can look at any results you want. So we've got, let's look at, say, the charge density, so Q3, and so that's electrons, and then QP3, and we can look at these as well as a function of applied voltage. So that's effectively a step through of the simulation. So I'm now going to show you a few sort of details in here that I think are worth noting. So you can change the electrical parameters in the electrical parameter window, and you can look at effectively you can set the electrical parameters in all layers. So the TiO2, the MAPI, and the Spiro. We're using a relatively complex. You'll have to read the manual a bit about this, but we're using a dynamic Schottky-Reed Hall model to model the trap. So you can perfectly well turn this off and put in some other recombination mechanism here, like 3 to 3 and 1 to 20 or something like that, and that should just run no problems at all. I'll put that back. What else? So you can play the electrical parameters to your heart's content is what I'm trying to say here. So that's that. Oh, it's also worth mentioning that just to simplify the simulation, and you can fine-tune to your heart's content. We've assumed there's a flat band structure across the device, so I've given everything a band gap of 1.6 eV. That helps the numerics. I don't want to get into numerics too much, but it just effectively makes your life a bit easier to run a more simple simulation than trying to simulate everything at once. So with sort of that in mind, I now want to talk about dimensionality of the simulation. So we've chosen here to do a 2D optical, 2D electrical, but quite often you might not want to run a full 2D electrical simulation, and this is one of the features that's quite nice in OghmaNano, is you can collapse the dimensionality of one of the simulations. So for example, if you look at the electrical model, we can look at the electrical mesh, and we can take out the X dimension and just solve the Y dimension. And if we rerun the simulation, And that was really fast this time because it was reusing the 2D generation profile already made and running a 1D electrical model. And now we've effectively got a 1D electrical model coupled into a 2D optical model. So it's quite nice because we've got the speed up of the electrical model, but keeping in the full 2D optical model. And if for example we decide, well, actually we don't want these triangles here, let's disable those. So we'll disable those, and now we don't really have a 2D optical structure because our 2Dness has gone because the triangles have gone. So what we can do is now collapse again the optical model to 1D. So if we go to the optical tab, optical mesh, we can take off the X dimension, and now we're just solving a 1D FDTD, and we run that, and the simulation almost runs instantly. And you can look at the FDTD snapshots in 1D, so you can look at sort of how the power's transmitted in the device. So I'm just going to reset those just for this demo. And I think the message here is that, and I'll also reset this one. I think the message here is that there's always this trade-off between accuracy of the simulation and speed. So if you just use a diode equation, it's going to be really fast to solve. You can solve it on paper, but you'll get less accuracy. But then you go to 1D Drift-Diffusion model, and that's a bit slower. You get a bit more accuracy, but you pay that cost in terms of simulation setup and simulation time. And then going to 2D models like this, you're again upping the difficulty and the amount of effect. You've got to pay to use the model. You've got to pay to set it up in terms of time. You've got to pay in terms of thinking about the results. So increasing the accuracy, increasing the complexity of the simulation isn't free. You, the user, have got to think. If it makes sense, if it actually helps your results, and so more is not always. Often more is less. It can be. So with that in mind, another question you might ask is why bother solve the full Maxwell's equations with this device? Maybe we can get away with a more simple model. So what about the transfer matrix method? Well, what you can do with Oghma is you can switch in and out optical models. So if we go to the optical tab and we look at the transfer matrix method, here it is, and you click run, it will apply the transfer matrix method, so literally the standard transfer matrix method, to this 2D structure, and it will give you where it thinks the absorption will happen. And we've only been running, and notice how quick that was to run. We've only been running one wavelength FDTD because it was quite slow. But now we look at this more simple method. We can turn on more mesh points. So let's turn on more wavelength points. So let's just go 20. Why not? We could do lots more than that, but and then rerun this. Excuse me. And effectively what we've got now is a wavelength sweep with the transfer matrix method, but in 2D. So we can look at where the charge is generated as a function of wavelength within the device in 2D. And notice this is actually absorption. So nothing's being absorbed in our triangles because they're TiO2. So this is the perovskite, but we can see, but fundamentally this is a 1D model because we're using the transfer matrix method now. So you can see there's no coupling really between the slices like you'd have in FDTD. So that's very nice, but what we can now do, which is quite nice, is we can go back to the electrical editors tab and click on JV editor, and here you can see it says charge carrier generation model FDTD, but we can set this to transfer matrix. And now, rather than using the FDTD model, it's going to be using the transfer matrix method to feed in to the Drift-Diffusion model. Now, the results, you can see already the results are slightly different. Where are we? JV. So we've got a bit higher of a JSC, and the reason for that is we've effectively changed the model completely. We've removed some of the assumptions. We no longer have lateral spreading of light and what have you. So the question when you come to do the simulation is, do I need that that 2D-ness, can I get away with it, and what price will I pay for using it, and what price will I pay for not using it. So that's really most of what I wanted to say. I think it's probably worth just having, I'll just show you another couple of features I think are quite nice, worth knowing. So in the absorption editor, we've got the absorption editor, which is a new feature, and you've actually got plots of each material and its absorption that you're modelling, which I think is quite nice. Another thing that's also quite nice, if you go to the optical model and light sources, you can change where the light source comes from. So you can change. So you can change if it comes from the top, the bottom, the sides, or wherever you want. So if you're doing if you're looking at sort of light or bifacial solar cells, you can set off the simulation running from the back of the solar cell. Another quite nice feature, I think I might actually run this, yes. So if we go back there and set the light coming from the top, and we'll also run an FDTD simulation. Where's my light source gone? Oops. And what we can do is we can slightly change the angle at which it comes from. So we can say slope it by 5 degrees, and then if we rerun that, now see, the mistake I've made now is I've told it to run like 20 wavelengths in FDTD, which is just going to take slightly too long for what I want to achieve. So I'll just put it back to 1. Oops. There we go. Let's run this. And now we can start looking at the results in whilst it's running. So what we've got here, effectively, we've tilted the light source by a few degrees, and you can see it's now propagating at an angle, but once it hits the solar cell, it starts to effectively bend around because of refraction. So you can check out performance at different angles and things like that. I think those are the main features I wanted to show. You can have a play yourself, so you can change electrical parameters, you can change optical materials, you can change the shape of this, so you can using the mesh editor, you can change what type of a shape you want there. You also change the number, of course, using the crystal editor. You can change the number of items you have, so that's 12 items. We can have 5 triangles, and spread them out a bit more as you like. So that's the end of the simulation. I hope you enjoyed it. Just say again, you can download this from OghmaNano.com-download.php. I'll put a link in the description. Thank you very much. I hope you've enjoyed this tutorial.